Okay, so this is section 5.4 and exponential functions. We're going to differentiate and integrate exponential functions. Just a little bit of review here. Log base b of y equals x. So the way I think about that is this to this power equals this. I always start down here and then I just go around like that. Some people think of it as the base, the answer, and the exponent. Your base is down here. That's the answer, and that's the exponent to rewrite it. So we want to be able to go back and forth between exponential and logarithmic because that'll help us. So log, and then I have this to this power equals that. Or if you want to think about it the other way, the base, the answer, and the exponent. Okay, here we have e, so we're going to use the natural log, so we don't need to write a base. I did that a little bit close there, it's a little bit awkward, but this to this power and equals, so that's y, and this is 5 over here. Should have separated those a little bit better, that's a little awkward. And if we want to move backwards here, we can do that. So 4 to the x power equals 6. 4 to the x power equals 6. Here we need to understand that's natural log, so that's base e. So that's e to the 5th power equals x this time. Okay. So e to the x, the green graph here, so that is y equals e to the x. So when x equals 0, y equals 1. And when x equals 1, y equals e. So those are the 2 points. E is 2.71828, which is pretty close to 3. So there it is. So this is saying that e to the x has a slope of 1 at the point 0, 1. That's not important to anything that we have to do, but it is something that's true. It is a way we could define the function e, would be a function that has a slope of 1 at 0, but or part of that. Anyway, so they're inverses of each other. An exponential versus a logarithmic. So if we set y equals e to the x and we find the inverse, we switch the x and y and then solve for y. And if we rewrite that in log form, we would get this. And so it's kind of just demonstrating that those are inverses and that it does the same thing here with a logarithmic switching it to an exponential. So we're trying to emphasize that they're inverses of each other. Okay. So that's what we're trying to emphasize there. And here are some techniques that we can use to deal with exponential functions and logarithmic functions. One is to rewrite it in the other form. So if it's logarithmic, write it in exponential. If it's exponential, write it in logarithmic. So that's one thing that we try to do. Try to get, if it's exponential, we try to get things in the same base. And another thing we can do is take the natural log of both sides. So those are all things that we could look at. So here, if we look at this, we just said these are inverses, and so when you apply inverses to each other, they kind of cancel each other out. Like you take the square root of x squared, you get the absolute value of x, but basically we're looking at getting x back. So these are going to basically cancel each other, and we'll have that 7 equals n. And similarly, if we had that the other way around, if we had the natural log of e to the 7th, that would work out the same way. And another way to think about that is actually use the properties of exponents and bring that 7 down here. And then e to what power equals e? Well, 1. So that's 7 times 1, which is 7. So that's another way to look at it. All right. And over here, again, you could think of it either way. First of all, you can think of it as inverses, so they eliminate, and so we're just left over with that. Or you could bring the exponent down in front, like we talked about here, and then the natural log of e is equal to 1. Okay? So, what can we do here? We can rewrite that as log base 2, answer exponent, this to this power equals that. Now, you may recall from your previous course we have a change of base rule. It's actually kind of easy to remember because you just switch it to the log of that divided by the log of that. But we're going to do the natural log. For one reason, it's one less letter. Remember, when we just write log with no base, that's the common logarithm, which is base 10. But in calculus, we tend to use the natural log pretty much most of the time. Change of base is what we're doing with that. And that's good enough for what we're doing. Or we could look at step 3 over there. And if we apply step 3 down here, we could take the natural log of both sides. So we would get this, and then we could use the properties of logarithms to move that x in front. And then we could divide both sides by the natural log of 2, and we would get the same thing. Kind of verification of the change of base rule. Okay. So here, what we want to notice is these are inverses, so those are going to cancel each other out, basically, nullify each other, just give us the exponent back. So that's just, and again, it'd be nice if you pause these and try and do something. Hopefully you have an idea of what to do with that. This is pretty much a review at this point. Everything except talking about the slope of the tangent line at that point. Okay, so here, hopefully you notice powers of 2, so that's 2 cubed, and so that's the same base situation. Okay. Now at this point, what we would do is we could, well, there's several ways to look at this, but one is just to set the exponents equal to each other. Now sometimes students will say, well, what happened? Did you cancel the 2's? We didn't cancel the 2's. The bases are already equal. So if the bases are equal and this is equal, then obviously the exponents have to be equal as well. Okay? So that's one way to think about it, but if you don't like that, we can also solve this another way. We could take the natural log of both sides. So if we take the natural log of this side and the natural log of this side, and we bring this down in front, and we bring this down in front, we would have 2x and the natural log of 2 equals 3 times the natural log of 2, and we could divide both sides by the natural log of 2, and then we would be back to here. If you don't take my word for it, that having the same base means we need to have the same exponents for those to be equal. Okay, and last thing before we get to some calculus here is solving. And so again, we're using these techniques here. So I'm going to try rewriting it in exponential form first. So the natural log, the base is e. Again, you should be pausing. I know some of you just sit there and copy this down. It's not really the same thing as thinking about it. So e to the 8th power equals this. And then we're going to divide both sides by 5. So pretty quick there. So that's just e to the 8th over 5, which is the exact answer. And we'll just leave it like that. And then finally here, we could bring down the exponent, properties of exponents. So that's going to be 2 natural log 3x plus 1 equals 8. Divide both sides by 2. So we're going to have the natural log of this equals 4. So e to the 4th power equals 3x plus 1. I'm going to flip the whole thing. Most people like the x on the left side better there a little bit. So that's going to be e to the 4th minus 1. And then we're going to divide both sides by 3. So that's it for that. So let's get into some calculus. So we need to memorize this. The derivative of e to the x is e to the x. So that's pretty nice. And e to the u, it's just the chain rule. So e to the u is e to the u times du. So I would just put on that the chain rule basically is what I would think of to remember this formula. Alright. So it would be nice if you could pause this and do these problems here. But so we're finding the derivative. So the derivative is 3 is just a constant, so that's not really affecting it. So basically you start off by writing down the same thing, and then, so that's the e to the u part, and then you multiply by the derivative of the exponent. So that's just going to be 2x. And then we're just going to rearrange that a little bit. So hopefully you're like, yeah, that's pretty easy. Now, when we move over to this next one, though, that's not a constant. That's a variable. And so when we see stuff, by now, we should be thinking of certain things. So this is a product rule, because it's a product. We're multiplying two things there. Oh, we're multiplying, yeah, but that's a constant. You could actually use the product rule on this. It's just when you take the derivative of 3, you get 0. So that goes away, so it doesn't even matter. But so we take the derivative of the first thing, which would be 1, times the second thing, and I'm going to rewrite that a little bit as 2 times x to the negative 1. Okay, so that's the first part of the product rule, plus the first thing times the derivative of the second thing. So when I do the derivative of the second thing, I start by writing it down, and then I multiply by the derivative of the exponent. So the derivative of the exponent, if we bring that down, that's going to be negative 2, and then we subtract 1 from the exponent, so that's going to give us that. Okay. Now if we look here, we notice that both of these have a e to the 2x to the negative first. So we can factor that out, and I'm going to rewrite that back the way it was, so 2 over x. Now we factored that out of here, that just leaves us with 1. And we factor that out of here, that leaves us with negative 2, and then it has x, and then this drops down, so that's over x squared. So we have x over x squared. So that x will cancel with one of those, and there we go. Okay, so hopefully that's working out pretty well for you so far. And this one looks a little more tricky. More going on in the exponent there, but we just go one step at a time. So we start by writing down, remember the derivative of e to the u is e to the u, so we just write down the same thing. Now again, I'm going to use the rewrite now to help a little bit. So there's e to the u times du. So we need to multiply by the derivative of the exponent. So this is good practice for our derivatives. Shouldn't be that big of a deal. The new part is just e to the u, and that's just writing down the same thing you started with, so not that bad. So this is a little bit involved here. So we subtract 1 from the exponent, so that's going to be negative 1/2, and then we have to use the chain rule because we have something inside there as well, composition of functions. So we have to multiply by the derivative of the inside. The chain rule is very important. So the derivative of the inside there is just 2x. Okay. So let's clean this up a little bit. So those 2's are going to cancel out. And if we look at the product here, we're going to have x times this in the numerator. And I'm just going to switch it back to the way it was. So e to the square root of x squared plus 1 in the numerator. And then this is going to drop down because of that negative exponent. So that's going to be over the square root of x squared plus 1. Okay, so you're just attacking that one step at a time. When you see e to the power, you just write down the same thing. So that's e to the tangent of x power. And then you're going to multiply by the derivative, that's e to the u. You just write down, so that's a pretty simple first step. Write down the same thing that you had. Well, here we had to use product rule, so that's not exactly, but these three right here, you just write down the same thing that you started with. And then the second step is to take the derivative of the exponent. Now the derivative of tangent, we should all have memorized. I'm actually going to write it in front instead of behind. So the derivative of tangent is secant squared. Although, I mean, maybe that's not the best because then you think that that's part of the angle, so maybe it would have been better over there. Actually, let's look at what that looks like. I think I like that better, actually. Here there could be a little bit of confusion as to whether that's part of the angle or not. So, okay. Find the local extrema. So here again, this is what I said, Chapter 5 can be a good chance for us to review some things. Obviously, we're reviewing some stuff from Chapter 2, derivatives, product rule, trig derivatives, chain rule. Now we're going to review something from Chapter 3, local extrema, minimums and maximums. So it's nice if when you see a question, you kind of know where it's coming from. That's coming from Chapter 3 in our book, graphing minimums, maximums, increasing, decreasing, stuff like that. So hopefully you kind of remember that we're going to need a derivative here. This is calculus. If you're not sure what to do, take a derivative. Okay? Not sure what to do, take the derivative. At least that's calculus. Now, actually, if you're not sure what to do, number 1 is skip it. Number 2, after you've done everything you know how to do, is take the derivative. Okay. So, again, we want to write down the same thing. So that's e to the negative 1/2 x squared times the derivative of the exponent. So times, so the derivative of this, bring the 2 down, so that's going to be negative x. Alright, so if we rewrite that, negative x e negative 1/2 x squared. So if we look at this, we set the derivative equal to 0. When is this equal to 0? It's only equal to 0 when x equals 0. Okay? This can never be 0. Now, if you look at this, this is always positive. There's no way to change, changing an exponent doesn't change the sign of something. So this part's always positive, so we don't even need to think about that. So if I plug in negative 1, negative times a negative is positive. We're positive over here. Then if we plug in positive 1, then this is negative, and so that's negative. Okay? So, if we look at this, we have a relative maximum at x equals 0. Now, it doesn't say where, it says find it, find what it is. So that would be the y value. So we want to go back and look at f of 0. So f of 0 is going to be e to the 0 power, which is 1. So relative max of x equals 0 at 1. So the answer to this question is actually 1. Now we want to keep that calculus, so we're going to need to say because f prime of x changes from positive to negative. And so if you think about that, that also tells us that f of x is increasing from negative infinity to 0 and decreasing from 0 to infinity. So a little bit review of increasing and decreasing also. And so one more thing down here. Find points of inflection. So inflection, points of inflection, that's also from chapter 3, and that should hopefully tell you that you should be thinking about a second derivative. So if we start with the first derivative, we have to use the product rule. So the derivative of x is 1. So we have 1 times e to the x plus x times the derivative of e to the x. That's just e to the x. Okay. Try to decide if I want to work with that a little bit more. I could factor out an e to the x, and then I just have 1 plus x. See how that treats us. Now we need the second derivative because we saw inflection in the problem. So if we take the derivative of this, the derivative of that is e to the x. So I don't know, I thought maybe that would be easier, but it looks like it's not going to be really. So the derivative of e to the x is just e to the x. So I'm just going to do this one here because that's not any easier. So the derivative of e to the x is e to the x, and the derivative of this, well, that's what we did there. It's the same thing. So the derivative of that's 1 times e to the x plus x times e to the x. Okay. So now we have 2 of these. So we have 2 e to the x plus x e to the x, and I could cross that off, but it just wasn't helpful. Here, we're going to set this equal to 0, and we could factor out e to the x, which leaves us with 2 plus x. So, if we think about where that's going to change signs, that's going to happen at negative 2. Okay, so at negative 3, this is negative. Remember, this is not going to change signs ever. Even if it has a negative exponent, that just makes it a reciprocal. That doesn't change its sign. So negative 3 would make this negative, make the whole thing negative. And if we plug in 0, this will be positive. Okay. Setting this equal to 0 is just to find this point, if you remember that. Okay. So we have a possible point of inflection and it says find the points, or point of inflection. So that's going to be negative 2, and if we plug negative 2 in there, it's going to be negative 2 times e to the negative 2. So that's going to be negative 2 over e squared. Okay, because f double prime of x changes signs, and we don't want to say from negative to positive, we just want to say that it changes signs. It doesn't have to change from negative to positive, it just has to change. And so we want to be careful about how we say that. And f of negative 2 exists. Okay? So that's combining the new thing we learned today, the derivative of an exponential function, with points of inflection, which we learned about back in chapter 3. Okay, and leading into the last page here, we're talking about integrating. And when we're integrating these things, it's going to kind of work the same way. The integral of e to the x is going to be e to the x, which should make sense because the derivative of that equals that. Now, plus a constant, because when you take the derivative of a constant, that's 0, so that's what's going on here. Now, with e to the u, it's a little bit trickier, and what we need to do there is we need to do u substitution. We need to substitute whatever the exponent is so that we just have e to the u. Okay? It's probably easier to see that in action, so we will just get there. Okay, so we just talked about substitution, u substitution. So anytime you have an integral of e, you want to let u equal whatever that is, a u substitution. Because we want to get it to be the derivative of e to the u du. Because then that's just going to be e to the u plus c, and then we can substitute it back in. So that should be pretty clear. So there's the exponent. So almost all the time it's going to be that exponent, I think. So the exponent there is 3x squared plus 1. And again, this chapter allows us a lot of review of stuff that we were supposed to learn first semester. So u substitution was something that we had at the end of chapter 4 as a technique to integrate. So then the first step is to figure out what you're going to let u be, which in this case is pretty much going to be the exponent. Then we need to take the derivative of that. So that's going to be 6x dx. Now we do have an x there, so that's good. We have the x dx. We don't have the 6, so we're going to have to divide both sides by 6. And now we can make the substitution. So if we substitute out the x dx for 1/6 du, so we have 1/6, and we'll have the du there, and then that's e to the u. So we're going to have e to the u du. That's really nice. And so if we take the derivative of that, that's going to be the integral of e to the u is e to the u. That's what we learned today. The derivative of e to the u is e to the u. And then plus c. And then the last step is to substitute the x's back in for the u's. So that's going to be 3x squared plus 1 plus c. Alright. And again, same thing basically. So u is, I don't want to say always, it's a little bit tricky to say always or never. So that's, I'm going to rewrite that as 3x to the negative first power. So I'm letting u be the exponent. So du is going to be negative 3x and subtract 1 from that. So that's going to be negative 2 dx. So that is right here. So that's good. Again, we don't have the negative 3. So divide by negative 3, negative 1/3 there. And now we're going to make that switch. So that's going to be negative 1/3. This is being substituted out for negative 1/3 du. And then that's e to the u. And that's the whole point. That's what we're trying to get. So if we integrate e to the u, we just get e to the u. I'm going to skip that middle step right here, and I'm just going to put the u back in. So that's going to be 3 over x, and then plus c for a constant. Don't forget the plus c. Don't forget the plus c. Lots of students do. Okay. Now, we have a definite integral. Remember, a definite integral is when there are numbers here. So let's think about what we have here. So this, first thing we want to do here is do rewrite. I told you rewrite's our friend, so we want to do that. Okay. Now the next step is let u be the exponent. Okay, so we have that. Now, there is no now we're going to take the derivative. So that's going to be negative 2 dx. There is no negative 2, so we have to divide both sides by negative 2. Okay? So now we're going to have the integral, and dx is negative 1/2, and this is e to the u du. Now we also have to deal with these numbers. We just switched this to u. Those are x's. This is all x. We need to switch it to u. we need to make it about u, not about your x. Okay? So let's make it about u. So if we make it about u, we're going to plug this in here. So negative 2 times 4 when u equals negative 8 when x equals 4. So this is going to be negative 8. And then we plug this in here. We have 0 times negative 2. That's just going to be 0. Okay, now we don't like these numbers to be reversed like this. We want them to be smallest to greatest. So we're going to flip that over. So we're going to move the negative 8 down here and the 0 up there. And hopefully you remember that when we do that, we need to take the opposite sign. So this was a negative 1/2, so it becomes a positive 1/2, the opposite. Okay, and now we're going to integrate that. So if we integrate that, 1/2, and then we have e to the u, and then that's going from negative 8 to 0. We don't need to switch it back to x because we switched the limits of integration to u's. It's all u now. We can just finish it. Okay, so that's going to be, I'm going to factor the 1/2 out, and then we're going to have e to the 0 minus e to the negative 8. Okay, and then probably should clean that up just a little bit and change that to a 1, and maybe 1 over e to the 8th, which is pretty insignificant, but we'll leave it anyway. Alright, and we're down to the end of our notes here, so let's see what we want to do with this. Suppose downward velocity is given by that for the first 5 seconds of jump, compute the distance fallen. So to find an amount, you integrate the rate. So this is a rate. So you integrate a rate, you get an amount. I've mentioned that before. It's kind of important. When you integrate a rate, you get an amount. So we want to integrate this. So the way we can do that is we can factor out that 30 first of all, and then we can integrate these separately. So we can integrate the 1, and this is first 5, so that's 0 to 5 dt minus 0 to 5 e to the negative t. Okay, any problems there? Is everybody all right with that? Looks fine. Okay, so now this should be pretty straightforward. Let's look at this. So here we're going to have u is going to be negative t, and du is going to be negative dt. Well, we can actually bring this back in for our negative dt and make that positive, and so then we do have negative dt. So that'll take care of itself. Okay, so that's going to be the integral of, although we still have to do the substitution, so that's going to be e to the u du, but we have to use this formula on these numbers, so that's going to change that to negative. So this is a little bit tricky. So by plugging 5 into this formula to switch it to u, that 5 becomes negative and 0 stays 0. So we need to flip that over, and that's going to make it negative again. So it became positive when we did the substitution, and it became negative because we have to flip that over. So that's a little bit tricky. So maybe I better write that down. So this is 30, and we did this. This will leave that as 0 to 5, 1 dt. And then this became positive. Then we got that with the substitution, so we need to flip it back. So that's going to become negative. And then this is going to be negative 5 to 0. And this is dt, and this is du. Okay. So if we look at that, I'm running out of room here, but we've got 30. And so we went across there, and now we're going across here, kind of jumping up here. So this is going to be t from 0 to 5 minus, and this is going to be e to the u from negative 5 to 0. Okay, so that's going to be 5 minus 0, plugging 5 in, plug that in, and then you subtract from plugging this in. And then here, I'm going to factor out that negative so it's maybe a little less confusing. So when you plug in 0, you're going to have e to the 0, that's going to be 1 minus e to the negative 5th. Okay? And so we have that. So that's going to be 30 times, this is 5 minus 1, so that's going to be 4. And we have a negative times a negative, that's going to be positive 1 over e to the 5th feet. Alright, and let's wrap this up. So, finally, take the derivative of this. Alright, so the derivative of the natural log, so we just go one step at a time. It looks a little bit messy, but we'll see what happens. So that's 1 over this. So that's going to be e to the x plus e to the negative x over 2. Okay? Now, so the derivative of the natural log is 1 over u times du. So we need to multiply by the derivative of this. So the derivative of this is just going to be e to the x. The derivative of this is going to be e to the negative x times negative 1. So that's going to be this. And then there's just 1 half, but so nothing's really going on there. Okay, so now we can treat this as a complex fraction. So we have a fraction and a fraction. This is 1 over 1. So we're going to multiply that by 2, and we're going to multiply this by 2. So these are going to cancel out. So now we just have 2 over this times this over this. So these 2's are going to cancel also. So now we're down to e to the x minus e to the negative x over e to the x minus e to the negative x. Alright? Plus. So it's always good to kind of take a look at what you've done, see if you made mistakes there. This one is the numerator, this one's the denominator. Now, technically, that's a complex fraction. Okay? Also, this was a complex fraction, this is also a complex fraction, because this would be 1 over e to the x. So since we have 1 over e to the x here and 1 over e to the x here, what we want to do is multiply by e to the x to deal with those. So if we distribute that, when you multiply two things of the same base, you add the exponents. So that's going to be e to the 2x. Now, when I multiply this times this, I add the exponents. So that's going to be negative x plus x is 0. So that's e to the 0. So that's just minus 1. Okay. Now down here, this times this, that's the same, e to the 2x. And this times this, that's going to be plus 1. Okay, so that kind of cleans up nicely. Okay, let's call that a day. It's about that time. Have a good day.